today is gravitation.
Okay. Thank you, Marshall. It's a pleasure to be here, and I really like it being in Korea my first time, and I'm honored for this invitation. So I'm going to talk about gravitation, okay, and we start pretty far back. Now, at the end of the Principia, Isaac Newton described gravitation as a cause that operates on the sun and planets according to the quantity of solid matter they contain and propagates on all sides to immense distances, decreasing always as r to the minus 2, 1 over r squared. In 1684, Newton proved that planets moving under the inverse square force law would obey Kepler's empirical laws. So they would travel around the sun with the sun at one focus of an ellipse. They travel around ellipses, and they sweep out equal areas and equal times, and the cube of the period is proportional to the square of the major or minor axis. I can't remember which one. Okay, and in 1685 he completed his lunar calculations that he started 20 years earlier. Okay. These stupendous accomplishments were published on July 5th, 1686 under the title Philosophiae Naturalis Principia Mathematica. In those days, all scientists wrote in Latin. Okay? Now, in the following centuries, Newton's gravitation met with a brilliant series of successes in explaining the motion of the moon and the planets. Some irregularities in the orbit of the planet Uranus remained unexplained until in 1846 they were used by Adams, an Englishman, and Leverrier, a Frenchman, to predict the existence and position of a new planet, the planet Neptune. So discovery of Neptune was probably the most splendid verification of Newton's theory. Discovered a new planet. One problem remained, and that was the perihelion shift of Mercury. Now the perihelion, there's the sun, and the perihelion is the place where Mercury comes the closest to the sun. That's called the perihelion. Okay? And it was off. It wasn't where it's supposed to be. It was off a little bit, and the little bit was tiny, very small. It was 43 seconds. Now, every angle has 60 minutes, and every minute has 60 seconds, so it's very, very tiny, and 43 seconds per 100 years, so that's really very, very small. Now, already in the 1840s and 1850s, astronomers had telescopes that were accurate enough to measure this. They could measure angles very accurately already, and they saw this, and they couldn't explain it. Now, to us, that looks like that's a small deviation, 43 seconds per century, but it bothered the astronomers. It was too much, too big, okay? And the first confirmation of Einstein's theory of general relativity was that it predicted this 43 seconds per century shift of Mercury's perihelion. So the theory has to be great if it could predict such a tiny, tiny deviation, okay? Now, general relativity is really Einstein's theory of gravitation, okay? It's not only a theory of gravitation, but it's the theory of the structure of space and time, okay? So it's much broader, space and time, and thus, therefore, a theory of the dynamics of the entire universe. The universe is embedded in space and time. Now, what's nice is it rests on pure geometry. It's indisputably elegant, and is of great mathematical and physical interest. All of these are true. Now, the revolutionary character of Einstein's theory of gravity lies in its change of our attitude towards space and time. Changes what we knew for thousands of years, okay? According to Einstein, the laws of nature are independent of the state of motion of an observer. In 1905, special relativity was constructed by Einstein, and that was where observers move with a constant speed, no acceleration allowed. It took him 10 years to allow acceleration into it to get the theory of general relativity. Okay? Now, general relativity incorporates the gravitational field. The gravitational field is the metric. I'll talk a little bit more about that. Into the structure of space and time. Okay? It incorporates the metric into the structure of space and time. Now, since gravitational fields vary from point to point, okay, that means that space-time has to vary from point to point. So space-time is varying, it's changing. Now, Einstein's brilliant hypothesis, his tremendous insight, is that the gravitational field is the metric, Gij, how you measure things in R3, so that's Euclidean 3 space, cross R plus, and that's the time axis. So R3 is x, y, and z, and R plus is t. Now, the mathematicians have really considered this before. The mathematical framework that deals with geometry that changes from point to point is called differential geometry. Okay? And the particular branch of differential geometry, which is called Riemannian geometry, is the basis for describing the gravitational field. The researches of Riemann 50 years earlier were crucial to general relativity. Okay? Riemann was a famous German mathematician. There's a lot of things named after Riemann. Now, according to Einstein, space-time is a four-dimensional manifold. So a manifold is something that looks like Euclidean space, sort of, and it's called the space-time continuum. Now, it's like R4, okay, x, y, z, t, but different. First of all, the pieces don't fit together to give an R4 globally. It's not like in this room. There could be all kinds of funny things happening. And even the local geometry around every point is not Euclidean or even flat. Now flat space is from special relativity, and the metric then is ds squared, the line element, is minus dt squared plus the x squared plus the y squared plus the z squared. In Euclidean space, that minus sign isn't there. Well, this is dead. The minus sign isn't there. Instead of minus dt squared, you have plus dt squared. So this is different. Okay? Now, space-time is covered by coordinate patches. I'm going to tell you really what a manifold is now. Space-time is covered by coordinate patches. So here, 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 little coordinate patches. And on each patch, there's a series of coordinates, x alpha sub I. Alpha goes from 0 to 3, 4 dimensions. And I is the patch on ui. Okay, the ui and xi are the coordinates there. Now, the basic geometry of the manifold, so that's what a manifold is, it's covered by patches. The basic geometry of the manifold, which mathematicians call its differentiable structure, okay, is determined by the relations holding between systems of coordinates in overlapping patches. So there's ui, the red thing, and there's ui prime, the green thing, and the overlap. What are the relations between the coordinates in ui prime and ui? That's called that's the differentiable structure of the manifold. Now, the main tool to study geometries of manifolds, okay, is what's called tensor calculus. Okay, I'll talk a little bit more about tensors as we go on. But the tensors are a generalization of vectors or matrices and things like that. Differentiation of tensors is complicated because the derivative of a tensor in an overlap region, that yellow region, okay, can depend on which set of coordinates you use. Okay? Now, the situation is remedied. It's fixed up. Mathematicians fixed this up before Einstein. And what is introduce in each coordinate patch, each ui, a special 3-indexed array of functions. So gamma has 1 index upstairs and 2 downstairs. And that's called a connection. All indices here go from 0 to 3. Okay? That's called a connection. All right? And the connection is required to transform in a particular way on the overlap regions. Okay? So here it is. So on an overlap region, ui intersect ui prime. So the prime connection of the prime is related to the connection of the unprimed by this formula. So it's the derivative of x prime respect alpha a with respect to xp, partial of xq with respect to xb, x prime b, and so forth. And there's the one the one without the primes. That's the connection that's defined in UI. And then you have this extra term added in there. But these are all relations between the coordinates in one patch and the other patch, and they have to have and that gamma pqr is the connection in the unprimed, okay? And the thing on the right is how you get the primed, okay? That's how it's required to transform. And now, when you have connection on your manifold, we don't say it's a derivative that you take. We say it's a covariant derivative. So that means coordinate invariant derivative. First of all, let's go back a little bit. A tensor, the right way to think of a tensor is that it has the property that if a tensor equation is 0 in one coordinate system, then it's 0 in every coordinate system. Okay? That's what's called a tensor. Okay? So tensors are more complicated things than vectors and matrices. They have indices of up and down all the way you want to go. So for example, if you have a tensor that has two up indices, you can think of that, if you like, as a matrix. Won't hurt in this case. So the covariant derivative, we don't write the ordinary derivatives. We put a delta sub a of that tensor AB is dA. That's the ordinary derivative of the tensor. And then it's the modification using the connection terms. Okay, gamma A alpha S ASB plus gamma B AT. And you see, whenever, now that we're going to make a rule here, a convention, whenever an index appears above and below on a line, then it must be summed from 0 to 3. That's Einstein's absolutely brilliant convention. Okay, without this, no mathematics and relativity could be done, because the equations would take the whole board. Okay, they're really out of sight. But this makes you believe you could do something with them. Okay, gives you courage to do it. Okay, now when the operations of calculus are well defined in this way, we say that the space-time has the structure of a differentiable manifold with connections. So it's a manifold, but you could also take derivatives unambiguously. Okay. Now in special relativity, the metric is what's called Minkowski metric. So ds squared, I'm down at line second from the bottom, ds squared is equal to minus dx0. x0 is ct. Everything has to be a distance, even so when t can't stand by itself, it has to be multiplied by velocity. So that's ct. And then dx1 squared, dr squared, dx2 squared, dx3 squared. So notice that the coefficients of all the d's are 1 or minus 1, constants, okay? Now ds squared always in geometry measures arc length, okay? Arc length is an invariant. The length of an arc from A to B, no matter what coordinates you take, it's going to be the same, okay? So that's an invariant. And in relativity, arc length is called proper time, okay? But it's really arc length, okay? Now in general relativity, the geometry, see that was special relativity, Minkowski space, where all the coefficients were plus or minus 1. But in general relativity, the geometry of space-time varies, changes from point to point, and it's represented by a metric tensor. So the metric is a 0-2 tensor, and so Gij depends on the point, x bar, and x bar is x0, x1, x2, x3. And the metric then is that star, ds squared is equal to Gij, dxi, dxj. Now remember, I and j are coming up and down in one term, so you've got to sum everything from I goes to 0, 3 and j goes to 0, 3. Pretty long thing, okay? Now Gij, so this is Gij is a symmetric 4x4 invertible matrix. So symmetric means you can reflect it across the diagonal and you get the same thing, okay? And at each point, here's what has to be also true. At each point, Gij could be diagonalized. Now, if you took some linear algebra, you know, you could diagonalize certain kinds of matrix. At least symmetric matrix can always be diagonalized, okay? Put it into a canonical form. and they could be diagonalized into this form. It's a diagonal matrix. Down the diagonal is -1, 1, 1, 1, and everywhere else is 0. Okay, so at every point you could do this, but you can't do it globally, even locally. You have to only at a point. Okay. Now, in order to get a theory that you could work with, okay, you have to have a relation between the metric, that is the distance, how you measure distances in that geometry, and they also have to be related how the operations of tensor calculus are done, and tensor calculus are determined by the gamma A, B, C. Okay, you need a relation between the metric, the distance, and differentiation. And this is established, the relation is established by a very important theorem, beautiful theorem in Riemannian geometry, and here's the theorem. Given a metric, it determines a connection by this formula here. Okay, now G upper AD is from this, the fourth line down, GAB times GBC is delta AC. So really, G upper AB is the inverse matrix, which always exists because at every point, the determinant, you can diagonalize the determinant's not 0. So there's 1/2 G upper AD, and then it's minus GBC comma D, so that's the BC component with D here, and then you permute the indices, and then you bring well, then it's GCD XB and GDB XC. Now remember, all of these, there's a D on the GAD outside, and there's a D everywhere on the lower part on the inside. So all of these things are summed again from 0 to 3. Again, to write it out is really, it's really complicated. It's really long. Okay, but this avoids that. And what's more, any covariant derivative of the metric, okay, so this defines the connection, and then the delta defines the covariant derivative, and that the covariant derivative of the GBC is equal to 0, okay? That is, the metric is covariantly constant, okay? Now, in fact, when you impose this connection formula and the covariant derivative is equal to 0, that's unique. So given a metric, there's only one connection that is covariantly 0, okay? That's covariantly constant, I mean, okay? And that's the metric, okay? So it's a nice theorem. All right. Now, general relativity is Einstein's theory of gravity. Okay, so let's now again say what Einstein's hypotheses are. I went up and down with it, but let's now get them out precisely. So first of all, the gravitational field is the metric Gij in four-dimensional space-time. So that's a revolutionary idea right there. Okay, and then the metric has to be symmetric. So we've talked about that already. You reflect it over the diagonal, you get the same thing. And at each point, you could diagonalize it in the canonical form -1, 1, 1, 1, and zeros off the diagonal. Okay? And finally, the equations of general relativity should be independent of any coordinate system. Coordinates are just an artifact, and physics shouldn't depend on what coordinates you take. Right? And so in that case, that means the structures that are independent of coordinate systems are called tensors. So the equations have to be tensor equations. Okay? And then you're guaranteed to have that independent of coordinates. All right? So these are the three hypotheses. Now, besides giving these hypotheses, Einstein wrote down equations for the gravitational field. And these are Einstein's equations in 1915. So that's 10 years after he did special relativity. Okay, it took him 10 years to figure this out. And so the Gij is equal to 8 pi times Tij. 8 pi, I'm taking units where the speed of light is 1 and Newton's constant is 1. Otherwise, that would be 8 pi times Newton's constant divided by the fourth power of the speed of light. So it's a very small constant. Okay? So the left-hand side depends only on the geometry. Only on the geometry. That is, it only depends on the metric and its first and second derivatives. Okay? It's a pure geometric thing. The physics is encoded in the right-hand side with the Tij. So if you want to look at Maxwell's equations, the Tij would be the Maxwell stress energy tensor. and then you have to supplement these equations with Maxwell's equations in that geometry. When you take ordinary physics, you know, even advanced physics, you know, second or third year physics, and you learn electromagnetism, it's always done in flat space. It's always done in the geometry of Minkowski space, but they're well defined in any geometry. Okay, so that would be. Now, if you want to look at a perfect fluid, like you want to study things in astronomy or astrophysics, then the Tij would be a stress energy tensor for perfect fluid, which we'll get to in due time. Okay, so now the Einstein tensor, the Gij, is made up of two terms. The first term is Rij minus 1/2 Rgij, and here's how you get the right-hand side of that equation. First of all, you compute the connection just as we just showed you on the earlier slide. Of course, it's given a metric, there's a unique connection, okay? And that's called, this connection is really called the Levi-Civita connection. So Levi-Civita was an Italian mathematician in the 1890s or something like that. And once you have that, then you compute what's called the Riemann curvature tensor, okay? And that's that Rij down there. So, I'm sorry, Riqkl. So it's one up index and three down. So it gets a little complicated. So it's the partial derivative now of the gamma iql with respect to xk minus the gamma iqk with respect to xl. Now that looks like a curl term. Do they use the word curl in Korea? What is it? Okay, they use the word. Okay, so that's a curl term. Okay, like Maxwell's equation. And then you have gamma ipk, gamma pql. Okay, remember now that those p's now are going from 0 to 3, so that's pretty long. That's, you know, four more terms. And then it's gamma IPL minus gamma PQK, and that's like a commutator. That's like a commutator. And if you look at it right, it really is a curl plus a commutator. And that's what curvature always is. Always is a curl plus a commutator. Okay? That's curvature. Now, given that Riemann tensor, then what you do is you get that 0,2 tensor by contracting on the middle index. So you see R, S, I, S, J. So that one, you're summing S goes from 0 to 3. Okay, so S is really not there. It's being summed out, so it's a 2 tensor. Okay, and that's called a Ricci tensor. He was also an Italian mathematician around the same time as Levi-Civita. And then, so that's the Rij that appears in the Einstein tensor, the first term. And then you contract the Ricci tensor with the inverse of the metric. So it's R, Gij, and, sorry, G upper Ij, R lower Ij. And you've got to sum those I's and J's from 0 to 3. So that's, again, a big long term. And that's called the scalar curvature. And that's the R in the second term of Einstein's equation, of Einstein's tensor. So that's pretty complicated, okay? Okay. Now again, I remind you, summation convention, repeated up-down indices are summed from 0 to 3. Now, Einstein's equations imply that massive bodies, see, on the left-hand side we have the geometry, on the right-hand side we have the physics. So Einstein's equation implies that large bodies, in fact every body, but large bodies, you could measure it, like the sun, deform the nearby space-time. So Mercury is the closest planet to the sun. Its space-time gets the most deformed because it's closer to it. It gets deformed as you go further away. It gets less deformed. So that's why Mercury had that anomalous perihelion shift, because the sun, this huge sun, modified the space and time nearby, and Mercury was just caught up in that new space-time, couldn't get away. Okay. And this deformation of space and time, that replaces what Newton had action at a distance, okay, that things would travel with infinite speed, you know, and which bothered Newton all his life, and he was attacked by Leibniz for that, okay. And so it replaces Newton's action at a distance by the fact that the planets travel along geodesics in the geometry due to the sun. So you have a geometry, a Gij, a geodesic, you have 2 points, so the geodesic would be the shortest distance in that geometry from point to 2 points, okay? Just like on a globe, the geodesic would be a great circle, you'd lie on a great circle, that's the shortest distance, okay? The geometry changes, changes the distance, is how you write the distance, of course a different metric. Now what's really beautiful is that Einstein's equations reduce to Newton's equations. So here they are, x double dot is equal to minus the gradient of phi of x. So that's like what you learn, F equals ma, okay? And phi is the gravitational potential, and phi is determined from the matter. The Laplacian of phi is equal to 4 pi rho, and rho is the density of matter, okay? So that's the matter, and then the matter determines the gravitational field. You put the gravitational field on the right-hand side of the first equation and solve for x. That's Newton's equations, okay? So what's beautiful is Einstein's complicated equations reduced to Newton's equations in the case of slow-moving bodies. That means that bodies whose speed is much, much smaller than the speed of light, and also weak gravitational fields. That is, the gravitational field should be the flat Minkowski eta ij, that always diagonal everywhere, minus 1, 1, 1, 1, plus a small error. Okay? So it reduces to the Newtonian equations. Now, in the Newtonian case, there's only one gravitational potential, that's that function phi. In the Einstein case, there's 10 of them. So it's remarkable that the 10 collapse down to just 1 in the physics, what we're used to here on Earth. Okay? So that's further, a nice thing about Einstein's theory. Okay, now two famous experiments. Of course, we just talked about the perihelion shift of Mercury. The perihelion is the closest point to the Sun, and in 1850 they noted that deviation. The perihelion deviation, as I said before, was 43 seconds of a century per 100 years. And when Einstein wrote down his theory and made the calculation, so it was 43.2 seconds plus or minus 0.05 per century. That's pretty close. Really pretty close, okay? And now there's another more famous experiment that stimulated the imagination of people, that didn't know anything about Newton's planets going around, around the Sun in an ellipse and all that. But this one they could understand. It's called the bending of light, okay? So in 1919, 4 years after the general relativity, the Royal Academy of Great Britain wanted to check Einstein's theory. Einstein predicted that the light would bend near massive bodies because the geometry is changing. Light has no choice. It has to go in that geometry. So what the British did was they sent 2 boats in the South Atlantic Ocean, one off the coast of Brazil and one off the coast of Africa. So one was on the east side, one was on the west side, just in case there was clouds on one side and they couldn't get to the ellipse. There'd be a chance that wouldn't be clouds on the other side because there's a big Atlantic Ocean. Okay, so here's what it is. So here's the Sun, and then there's the Moon over there, and then here's a guy standing, an observer on Earth is standing right at that black dot. Okay, and during the eclipse, you could see the stars because the Sun is not so bright during an eclipse. In fact, the Sun is blocked out. So astronomers knew that the star had to be all the way over on the left. They knew that star. They knew where it's supposed to be. And then when they measured during the eclipse, they saw the star's image over there because the massive Sun bent the light. Okay, bent the light. Okay, and then that. So here's a picture of the eclipse. I put in a little picture of the eclipse. And of course, they didn't use those kind of boats. They had more modern boats in those days. But I thought it's just a little funny to put those boats in. Okay, and that instantly made Einstein a household word. Everybody knows Einstein. Everybody that went to school, through high school or something like that, knows Einstein's name. Back from 1919 to today, so that's almost 100 years or 91 years or something like that, 81 years. So it made him, and the newspapers would say, Einstein proves Newton wrong. You know, that was the headlines of the papers and stuff like that. It was kind of funny. Okay, so these were two fantastic things. So Einstein, not only did he write equations down, but he told the physicists where to look for to check the theory. He told them what experiments to make. So it was really a remarkable person, remarkable scientist, remarkable person too, actually. Okay, now there's an interesting feature of Einstein's equations that's not present in the Newtonian case. Okay, and that's that Einstein's equations admit black hole solutions. And let me explain how you get that. So now let's look at the case where Gij is equal to 0. So there's no. So we're looking at a star, make it a spherical star, and we're taking no matter outside. So you want to look at the gravitational field just due to that star and forgetting about any other matter. So you look for, the star is symmetric, so you look for a radially symmetric solution, and this was found in 1917, so that's 2 years after Einstein's theory, by the German astronomer Schwarzschild, who was a friend of Einstein in Berlin. Okay, and he was talking to Einstein, and he understood Einstein's theory right at the beginning, and he made this calculation. In fact, this is a very interesting story. 1917, the First World War was on. It was the middle of the First World War, and Schwarzschild, you know, there was all these patriotic people just ran to be soldiers and fight for the country. And Schwarzschild quit his job and went to join the army. Okay, and he got very ill in a hospital, and he was dying, and he wrote out this paper with this solution, the most famous solution up until the 1960s, and sent it in to Einstein. Okay, so sort of like, if you know the story about Galois, you know, he wrote this stuff down the night before he was killed in a duel. This is analogous to it. Okay, so here it is. So here's the metric. So here's a line element. So the coefficient of dt squared is 1 minus 2m over r. M is the mass of the star. And then the coefficient of dr squared is 1 minus 2m over r to the minus 1. Okay? And then you have the angular variables that are harmless, just r squared times d theta squared plus sine squared theta d phi squared. And that's the standard metric on the unit 2 sphere. So if you take, you know, first course of differential geometry, you see this second week or something like that. Okay. Now notice that at r equal 2m, the metric gets funny. The dt squared is a 0, and the dr squared blows up, becomes infinite. Okay, remember the r squared blows infinite at r equal 2m. Now r equal 2m is a special place, and it's called the event horizon, or it's called the Schwarzschild radius. And here's what the function 1 minus 2m over r looks like. At 2m it's 0, and then after that it goes negative. So for r less than 2m, in other words, inside that Schwarzschild radius, that function changes sign. Okay, it was positive outside, becomes negative inside. So in the region r less than 2m, as we have over there, r becomes what mathematicians call a time-like coordinate, and t becomes a space-like coordinate. That is, inside the Schwarzschild radius, space and time interchange. So that's a radical idea, space and time interchanging. But inside black holes, things are very wild. Okay, so now you can't see this black hole stuff in ordinary coordinates that Schwarzschild wrote down. That you can't see it. But in what's called Kruskal Coordinates, Kruskal was a famous American mathematician. One sees that the Schwarzschild sphere, okay, so that's a 2-sphere, has a 3-sphere, excuse me, has the physical features of a black hole. Okay, you can't see it in regular coordinates, but in these Kruskal coordinates, which you look up in any book on relativity, you'll see that. So it has physical characteristics of a black hole. So light and nearby particles can enter, but not escape. A black hole is something that's so dense that nothing could escape. Things can fall in, but nothing can get out. Just like if you're on the moon, you could jump 7 feet in the air because the smaller mass than the Earth. As the body gets smaller and more dense, then you could jump less and less. And in a black hole, you can't jump anywhere. You can't get out of that place. You're trapped. Okay? So light and nearby particles can enter but not escape. And there's an intrinsic singularity at the center. Intrinsic means that you can't remove it by a change of coordinates. You see, now Einstein's equations are tensor equations, so it's possible, those are bad choice of coordinates, and you know, with a coordinate change, you could remove that singularity, but that's not true. See, for example, in the plane, in xy plane, let's look in r and theta coordinates. Now, when r is equal to 0, the coordinate system breaks down. You can't give a theta. But there's nothing wrong with the origin, right? It's just if you change coordinates to xy coordinates, everything's fine. But you can't do that here. You can't do that. You can't remove that singularity. Okay. So now, then in 1964, some remarkable solution happened, and it was discovered by the New Zealand mathematician, mathematical physicist, I guess, Roy Kerr. And he found a gravitational field outside a rotating black hole. Okay? Now, all astronomical objects rotate. Okay? The Schwarzschild black hole doesn't rotate. Okay? So what he found was a two-parameter family of metrics. That means it depends on two constants. And they depend on the mass of the black hole, that's m, and the angular velocity of the black hole, that's a. Okay? And here's there's the line element for the Kerr metric. So it's 1 minus 2m over v dt squared, and then you have 4m ar sine squared over v, and then you get a mixed term dt d phi, and that's due to rotation. And then you get a dr squared term, and then you get all these other terms here, the angular terms and stuff like that. Now that v is harmless. It's r squared plus a squared cosine squared theta. That's a fine function. It doesn't do anything crazy. But the delta, you see, which is the 1 over the coefficient, the delta is in the numerator, the denominator of the dr squared term, and if we take the case where m squared is bigger than a squared, that's called the non-extreme black hole. Okay, this is the right generic one. The roots of delta, there are two roots then. If m squared is bigger than a squared, you get two roots, m plus or minus squared of m squared minus a squared. The r plus, the one with the plus sign, corresponds to the event horizon or the black hole. Now you see that was just like in the Schwarzschild case where the coefficient of dr squared becomes infinite. That defines the black hole. Now the r minus, is what's called the Cauchy horizon, and that's inside the black hole. The future is not necessarily determined by the past. So things get really, out of control inside the black hole. Okay, now the Kerr metric is axisymmetric, so there's an axis and it's rotating about some axis, and it's stationary. It doesn't change, it doesn't run around. It's just turning and staying there. And the region where the vector d by dt, so that's 1, 0, 0, 0, is time-like, is where the coefficient of the dt squared term is bigger than or equal to 0, and that's the coefficient of the dt squared term. But the open region where d by dt is space-like, so when the inequality is reversed, and you have to be outside the black hole, is called an ergosphere. So there's a region outside the black hole that's in red over there. See, that's the picture where the black hole is rotating around. And then the ergosphere, it touches the black hole at the north and south poles. And if you look at it from top, it's just a ring around there. Okay, that's called the ergosphere. Okay, that's a very interesting feature, only of rotating black holes. And now, if you take p bar, the vector p0, p1, p2, p3 is the 4 momentum. Everything is 4 now because time and space are equal coordinates of a particle. Then by mechanics, p bar is always a time-like vector, always. Okay? Now the energy density, capital E, is defined by the inner product with p bar and the vector d by dt, and the inner product taken in the Kerr geometry. So inside the ergosphere, because d by dt could become space-like, and so you're hitting a space-like up against the time-like, so it's possible that E can become negative. Okay? And the energy, which is the integral of the energy density, the script E down here, the fourth line from the bottom, is not necessarily positive. So the energy is not necessarily positive. Okay? And that's the source of much mathematical difficulty. You can't use what's called energy methods, okay, to solve your equations. You have to be, you could use them, but you have to work infinitely harder than usual. Now, there's an important question that comes here. You want to prove the stability of the Kerr metric under perturbations. Okay, that's an important problem. You want to investigate the stability of various fields in the Kerr geometry. So the first thing would be scalar waves. So they're just, scalar wave equations. And then there's the Dirac equation. The Dirac equation, again, is a linear equation. It depends on the geometry. Dirac equation is the general relativistic extension of the famous Schrödinger equation from quantum mechanics. And then you have Maxwell's equation in that geometry. And then you have something called gravitational waves. Okay, so there are these four different physical situations, and you want to see how these are. Are they stable in the Kerr geometry? That is, if you look at the initial value problem for these things, any one of these four equations, where the background metric is fixed to be a Kerr metric, you want to start out with initial data that's outside the black hole, that's compactly supported, that it's zero outside of a compact set, and you want to follow the solution, and you want to show the solution goes to zero. That would be linearized stability. Okay? So what's really interesting and actually amazing, all of these problems can be described by one single equation, a one-parameter family of second-order wave-like partial differential equations, which is called the Tokarski Equation, and that goes back to 1972. Dekosky is one of the two people who are doing the theoretical work on the gravitational wave detector that the United States spent $2 billion so far already on. Okay. So he was very good. That was his thesis, actually, PhD thesis. So here's the Dekosky equation. So it's kind of complicated. So it's d by dr, delta of d by dr, and then so forth and so on. And then there's the dt squared term, and then there's dt, and then there's another dt term. And what's happening now is there's another parameter besides a. Remember, a is the angular velocity of the black hole. M is the mass. But then the Dekosky equation has another parameter. It's just a constant. So m is the mass of the black hole. A is this angular velocity, and delta is what we had before, m squared bigger than a squared. But now we're outside the black hole, so we don't worry about 1 over delta going to 0, having a 1 over delta. The parameter s is called, the physicists call that the spin. Okay, that's the spin. And what's amazing is when s is equal to 0, this equation governs scalar waves. When s is equal to half, it governs the Dirac equation. When s is equal to 1, it governs Maxwell's equations. And when s is equal to 2, it governs gravitational waves. Now, when I first saw this equation, which was maybe 15 years ago, a physicist at a conference showed it to me. I just didn't believe it. How can you? All you're changing is that one constant, and you're getting all these four different physical things. How can that be? It's impossible. But I went back and I studied the thing for 2 weeks, and it's right. Okay, it's really right. Okay, a remarkable thing. So the main problem is to solve the initial value problem for the Dekosky equation with compact supported initial data outside the black hole, and show that the solution decays to 0 as t goes to infinity uniformly on compact subsets of R3. And that's linearized stability. That's already a challenging problem. One wants nonlinear stability, but that's 25, 30, maybe 50 years away. Okay, so my collaborators and I solved the problem for s equals 0 scalar waves and s equal to a half for the Dirac equation. And we're currently working on the s equal to 2 case. That's the stability of gravitational waves. That's orders of magnitudes harder than the s equals 0 and s equal 1/2. It looks like they should be the same, but they're not. They're not. Okay, so that's the current state of that. Now there's something called the Penrose process. So that's extracting energy from a rotating black hole. So remember that the black hole is a no-escape region. Nothing comes out. Now in 1969, the mathematician Roger Penrose, British mathematician, proposed a way of extracting energy from a rotating black hole. Now, he just proposed it. He had no, it was a thought experiment, okay? And here's what he proposed a way of getting energy out of a black hole. Here's the idea. Consider a particle of energy E0, that's the green one on the left down there, and that comes into the ergosphere, the red thing, okay? And inside there it splits into two particles, one of energy E1 that goes out and escapes to infinity, and the other one, E2, goes into the black hole, that other particle, and can't get out, stays there. Okay, the particle of energy E2 enters, the particle of energy E1 escapes to infinity. Now, the guy who goes inside, he said, should have energy E2 negative. Now, by conservation of energy, E0 is E1 plus E2. E2 is negative, so it's the right-hand side is less than E1, so E1 is bigger than E0. So you're getting more energy out than you put in. Now, what the heck? How could that happen? Where is this coming from? How can you do that? Well, the energy is extracted from the black hole. Where does it come from? It comes from the rotational energy of the black hole, which slows down. You're getting the energy from slowing down the black hole. So that's pretty interesting. Okay, pretty smart guy to think of that. Now, in 2007, my collaborators and I proved rigorously that you could really do this. Okay, it really could happen. You have to fine-tune things, but you can really do it. Now, earlier than that, the Russians, Starobinsky, Zeldovich, and so on, showed this. They jumped on this problem, showed numerically and by approximation asymptotic expansions in the 1970s that you could do this. But we proved it rigorously. Okay, let's change topics now. Last topic, well, next to last topic, shock waves and general relativity. So what are shock waves? Shock waves are violent physical processes that are ubiquitous in nature. They're all over in nature, okay? And they appear on many different scales. For example, the combustion, scale of combustion, automobile engines, shock waves are going on inside your motor. And jet planes, when a jet plane goes faster than the speed of sound, you hear that bang down there. That's a shock wave coming down to Earth. And then atomic bombs are shock wave explosions. Bigger than that are volcanic eruptions. And then bigger than that are supernova explosions of distant stars. So they come on all different scales. Okay, shock waves are all over the place. Now there's something called the shock front. And so the medium, whatever you're looking at, undergoes sudden changes in pressure, density, temperature, and so forth. So on one side of the front, there's certain pressure, density, and temperature. On the other side, there's another one, okay? Shock wave connects those two. And they're described by nonlinear partial differential equations that are called conservation laws. And shock waves are classical, and they go back to Riemann in the 1850s. So here's another great thing Riemann did. He did 10 great things. Okay. So general relativistic shock waves were first constructed by my collaborator Blake Temple and myself in the 1990s. So here's the picture. So inside that circle is an expanding shock wave. And inside there's one metric that is one gravitational field, and outside there's another metric, a second gravitational field, and we match those metrics across a discontinuity, that circle, of the fluid variables, a shock wave for the fluid variables. And our solution models what's called supernova explosions of distant stars. You have to go to general relativity for supernova explosion. That could also be used to model the Big Bang expansion of the universe. And it's different than the standard Big Bang of cosmology. How's it different? Well, the standard Big Bang, at t equals 0, there's no matter, there's no mass at all. Okay, nothing is there. That's before God created the earth, if you like. Okay, at t equals, heavens, I mean, at t equals 0, there's no mass. But for any t bigger than 0, any t bigger than 0, the mass goes to plus infinity. Now, that's very unsatisfactory mathematically. How can anything go from 0 to infinity instantly? Never saw a function that does that. I mean, how can that do that? So our Big Bang model is due to a shock wave explosion. So we say that the expansion of the universe is a shock wave coming out of a point into an ambient space-time where the leading expansion is a shock wave. So at each t equals 0, our mass is finite. At every time it's finite. And there's the picture, and there we are. And the shock wave is going out. And all the other things from the Big Bang, the standard model, it obeys, okay, but it doesn't have this bad feature of going from 0 to plus infinity instantly. Okay. So now the last topic is what's called the anomalous acceleration of the universe. So in 1927, the astronomer Edwin Hubble showed that the universe is expanding. Distant galaxies are receding from each other. Okay, there's no doubt about that. And the expansion is modeled, the mathematical model for it is by assuming what's called the cosmological or Copernican principle. That is that the universe is homogeneous, so every point is like every other point, and the universe is isotropic, so if you look in any direction, you see pretty much the same. But you have to look way out, okay? I mean, you know, you can look to the sun, it's different than looking to the right of the sun, but you have to go way out on the biggest scales to do that. So these hypotheses are unverified, simplifying assumptions, okay? They're unverified, simplifying assumptions. And they lead to what's called the standard model of cosmology, and there's that metric there. So ds squared is minus dt squared plus r of t squared times, again, the standard metric on, no, it's dr squared plus r squared, the standard metric on the two-sphere. So the only thing is that capital R, everything else is not changing. And that's called the FRW metric, Friedman, Robinson, Walker, three physicists who independently came up with this. And that R is called the expansion factor, and the universe is expanding, so R dot, the derivative of R with respect to time is increasing, okay? It's positive, so it's increasing. So at each time, t bigger than 0, that dt squared goes out, the R of t squared is a constant, so it's just the flat universe, okay, at each fixed time. So it's flat universe expanding out. And there's another thing interesting, the Hubble constant, that's h of t. It's really not a constant, but it's called a constant. It's r dot over r, okay? That's the Hubble constant. Now, in 1998, astronomers announced the discovery of something astounding, that the universe is actually accelerating. It's not moving out, but it's getting faster and faster as you go further out. It's accelerating. Okay, and that's called the anomalous acceleration of the universe. And that's one of the great problems in physics. What the heck? How's that happening? How's that happening? So, and this was discovered from astronomical observations of these supernova explosions, these huge explosions. How do they do it? Well, if you let z be what's called the redshift factor, that's lambda 0 over lambda e minus 1, and lambda e is the radiation wavelength at the source, the emitted, that's the E, and lambda 0 is a radiation wavelength that the observer sees, and that's the O. And the redshift factor is actually easy to describe. So you see, you have two elements, let's say carbon and deuterium or something like that, and you look at them in a spectroscope here in the lab, you know, on Earth, and you see there's a certain distance between them in your spectroscope. But then when you take your telescope and point it out to a distant star, because the star is receding, there's a change. It gets bigger. It gets longer, okay? It's just like, you know, at night you hear a car going by, a police car coming out, and then it changes, all right? Because it's stretching out its wavelength. So that's the same thing. It's called the Doppler effect, really, but in astronomy. So that's Z is the redshift factor. And L is the luminosity. That's a little bit technical. I don't want to go into it here at this talk. But it's okay to think of L as brightness, okay, as brightness. And here's what happened. The astronomers make a plot of Z versus L. They look at that star. They see its redshift. They measure its brightness. And in the standard model, it must be a straight line. It must be a straight line. You can't get away from that. But when they observe those supernova explosions, they're seeing it's not a straight line. It's deviating off from the straight line. And that means the standard model cannot be correct because it's not meeting the experiments. It's not meeting observations. Okay? So you have to kill the standard model. All right? Now what the physicists do is they modify Einstein's equations by adding what's called a cosmological constant, and that's lambda down there. That's an artificial correction term which speeds up the expansion rate. So ordinary Einstein's equation, Gij is equal to Tij, it really should be 4 pi, but that's not irrelevant. But what they modify, they change Einstein's equation, they put lambda times Gij in there, okay? It's really, mathematicians call this a fudge factor. I don't know if that comes up in Korean, a fudge factor. If maybe not, okay. Anyway, so that's a change just to make things work. And that's the only way to preserve the cosmological principle, which they love, and to account for the anomalous acceleration. No other way. You have to add that on. And there's no physics behind it, and it leads to a concept of dark energy. Dark energy is an unobserved anti-gravitational force. Nothing in the world was ever anti-gravitational before, and it certainly hasn't been observed. Okay? So, whoa, what the heck happened here? Okay, different explanation for Temple and I. Temple, same guy with the shock waves, and this appeared in 2009. And our explanation is based on a new expanding wave solution of Einstein's equations. We don't need a cosmological constant, and we don't need dark energy. Okay? The idea is to embed the standard model of cosmology into a one-parameter family of expanding wave solutions of Einstein's equation. So one parameter, think of a curve, that's a one parameter, and every point on that curve corresponds to a space-time. Okay? They're all different, okay? And the metric only depends on r over t, okay? And that's called a self-similar variable. And the parameter that it depends on is called a, we write it as a, it's called the acceleration parameter. And when a is equal to 1, you get the standard model. So here's this one parameter, here's this point over here, a equal 1. That's the standard model, the only homogeneous and isotropic space-time. Now, we prove that the redshift versus the luminosity relation is as there. L is equal to constant times z plus a squared minus 1 z squared plus a squared minus 1 3a squared 506 z cubed. And then the error term is something bounded times a minus 1 times z to the fourth. When a is 1, you see all the terms cancel except the first one, and you get the linear relation, what's true for the standard model. Okay, L is equal to c times z. And here's the standard model. Now, by adjusting a, we could obtain the leading order quadratic and cubic corrections to the standard model. And so we match their graph with the a for the quadratic thing, and then the cubic term allows us to make a prediction. We say, well, look more carefully at those things. See if you can get that third order term. Does it agree with ours or not? It's a prediction. Might not. But anyway, we can make a prediction there. So we don't need dark energy. Okay? Now, the physics behind our theory is the following. So there's t equals there with the Big Bang. And then you go up to 300,000 years after the Big Bang. And that's called the pure radiation era. So that's when electrons and photons were interacting with each other, and it was very hot and dense, and you can't see, and their light can't come out. And then after that, after 300,000 years, everything cools down, and you go to zero pressure, and that's where we are now, our present time, 12 times 10 to the 9th years after the Big Bang, something like that. Okay, we don't really know, but it's far. And it's based on the mathematical theory of conservation laws. Nonlinearities alone can generate dissipation that in time will drive a chaotic disturbance into a non-interacting self-similar expansion. So we argue that the complicated behavior in the pure radiation era, that's the red stuff up there, is driven by the high sound speed. Oh, that should have a square root. It should be the square root of c squared over 3, that first one, in the equation of state p equals c squared over 3, that comes from the initial disturbance of the Big Bang. So it's c divided by the square root of 3. That's a big number. C is a big number. So it's driven by that. So it's like the orderly concentric circles of waves which emerge in time on the surface of a pond after you drop a rock onto the surface, and there's a plunk, and then there's something more, and then all of a sudden all these nice concentric circles come out. That's the self-similar circles that are coming out. It's analogous to that. Okay? Now, the stars and galaxies and clusters of galaxies are evidence of small-scale variations that violate the cosmological principle on smaller scales. Our solution violates the cosmological principle since the center of the expansion wave where we are is distinguished. Okay, but we argue there could be an even larger length scale than the clusters of galaxies on which local decay to one of our expanding wave occurred, and we happen to be at one. Okay, so that's what we say might be happening here. So the cosmological constant and dark, so that's the problem. People say, well, you have the Earth as a special place. That's not so great. But the cosmological constant and dark energy have major problems too. There's one, it's called the fine-tuning problem, and that's motivated by the enormous discrepancy between the theoretical prediction of the cosmological constant lambda and its measured value. 60 orders of magnitude smaller than the theoretical prediction. So it's 10 to the minus 60. That's an unbelievably small number. I mean, there's nothing, 10 to the 60th is enormously big number. Like I like to say 10 to the 22nd, which is the number of stars that we could see, there are more of those than particles of sand on Earth. It's 10 to the 60th is way bigger than that, okay? So that's a serious objection, right? And then there's something called the cosmic coincidence problem. Why do we live in an era when the density of dark energy and matter are almost equal? You could read about that on the NASA web page. And I think I'll leave you with that, okay? I finished.
We have time for some questions.